Speaking about recording, I should. Speaking about recording in progress. Okay. Hello, João. So, speaking about recording, I should put the video of the first lecture, the last lecture online. The first is already there. I will do that possibly today even. So you'll have that video soon there. For Ilari, actually, for you, it's good for you to see because you were not. I think you were still in Italy last week. Right. Okay. So let me go directly to the. One thing that I wanted to inform all of you, which is so about the take-home examples for this module 2. So I will put the same weight to all of them because the contents are very important in all of them, equally important. And also from the experience of the first one, you put a lot of effort in all of them. So I think it's fair to split the weight of each of the exercises evenly. So this is a slight difference, unless someone just now says I totally disagree with that, because it was written in the like in the proposal of the module, 30 plus 70%, but now it will be 3 or 2, but I think it will be 3 with a 1/3 weight for each of them. Right, so now lectures here. So I'm opening everything from scratch here because it's to stop it with theory first. Okay, right, so we stopped, and I have to share the screen, of course. So products. I have to share the screen. It's not sharing. Okay, so once again, if you see any movement there, because I don't have, I cannot see the Zoom, I cannot see Zoom, oops, I cannot see Zoom from here. So if you notice anything, someone chatting, something, please.
You could just minimize those open windows.
I can.
Okay.
Like this. Let me put here. So it, like here. So. Okay, does it bother anything there? It's okay? Okay.
You can put that on the side. If you go to view options on the top.
Where?
On the top of the screen, you are viewing the Antonius. No, at the center top, there's a view option. Yeah, you click on view options. And there's nothing. I thought there was.
It's already in full screen.
Side by side.
This?
Yes.
Ah, okay.
You don't have to move around the.
Yes. Yes, that's true. Maybe that's good. Okay. Is it? Do you guys can see it properly? Or do you prefer the previous view? Okay, good. So that you can also see what's going on there. Okay, good. So please just move around. So we are just fixing here the geometry of the room so that everyone can see it. Okay, so a little recap of what was before. So we learned. So the main thing that we learned in the previous lecture was how to calculate the dimension of SUN representations by using Young tableau. We saw there were 2 possibilities. One was putting the Young tableau or converting it into what is called the standard tableau, and the number of different standard tableau would give you the dimensionality of the representation. But that if you go up in the rank of the group, that would become quite messy procedure. So the second and the better procedure is to use this hook procedure, where you count basically the number of hooks and also the number, a number that we call P, which for a given SUN, let me recap, for example, starts in the top left box, you always start with a number which is equal to n of SUN. And then when you go down, you reduce 1 unit. When you go to the right, you increase 1 unit. So as for example here, it's if this is SU3, then it goes 4, and if you continue 5, 6, 7, 8. If you go down here, this has to be 3, 2, 1. It has to stop in 1. 4, it's 4, 2, 4, 3, 2, and so on. So this is the procedure. And also, you also learn how to count the hooks. So this hook factor. So you draw a hook and you count the number of boxes. So there is when you have the corner of the hook, that the number associated to the box where you have the corner will be the number of boxes the hook passes through. So this blue one is 1, 2, 3. The red one is 1, 2, so it's to here, and the green one is 1 only. And then you compute the dimensionality by putting P over H. So here it's the so the formula was given above. So where is this? Here. So the dimensionality is P over H. And this gives you, in a straightforward way, the dimensionality of the representation, the SUN irreducible representation. Okay, also recall that when you have n boxes, a column of n boxes in SUN symmetry, this is a singlet. This represents a singlet, and typically they are eliminated. You remove them and you replace by 1. You just write 1, which is the label of a singlet field. Right, but now that we have learned that, I will give you another set of rules now, which is to do the most important thing of this group theory part, the calculation of tensor products. This is where indeed it's rather important, because when you're building Lagrangians, and this is valid not only at the renormalized level, but also if you build higher dimensional operators, you can build with n fields, and if they sit in non-trivial representations of a given symmetry, you need to know whether a certain Lagrangian term, or in other words, you need to pick up the singlets, because the Lagrangian is a singlet. So you need to compute the tensor product of those representations and pick up the singlets, and that will be your Lagrangian term. But if you do that in a normal way, just contracting indices, if it's about SU2, maybe it's not difficult, but if you start going up for larger SUNs, then it becomes rather complicated to do and likely to miss the calculation. Also because you need to know whether you have symmetric, antisymmetric indices, or a mixture of both, and that it's for that Young tableau is made. So I start here saying that Young tableau are particularly useful in decomposing tensor products. So let's and in fact in representations, tensor of 2 SUN representations in a sum of irreducible representations of the same SUN. We are fixing the symmetry to be SUN. So what are the rules to consider now? So the first one, which is actually rule number 4, because I'm also counting the rules that were introduced in the previous lecture. So the first thing is that you choose one of the Young tableaus. Typically, you choose the smallest one. I will make it more concrete. And fill in the boxes with A, B, and C labels, such that in the first row you have A's, in the second you have B's, third C's, D's, and E's, and so on. So this is the same Young tableau that we introduced in the previous case, in the previous lecture. But this is what you do. You fill in the boxes, following this rule. I think this is clear enough how it is here. Now, this is the part that only when you see an example, you will understand what is meant. You need to stack the A boxes So you will stack all these A boxes of the label diagram. Recall that you have two. Here, this is tensor product with some other diagram, something like that. And you will stack these A's first in all possible allowed manners in the other diagram. So you will have now several possibilities which will sum directly. It's a direct sum. And this is what I write here. Stack the A boxes of the label diagram onto the other while keeping it a valid Young tableau. So obeying all the rules that we have introduced previously, like you cannot have rows that are longer than the above one. You cannot have columns that are bigger than that have more than n boxes. And also, these Young tableaus are left justified. And then you take the direct sum of all the diagrams where you have stacked the A labels. And you repeat this procedure for B boxes, for C boxes, D, and E boxes, all of them. Now, you will read each diagram backwards, starting with the first line, and then the second one, and then the third one. And delete all diagrams where at some point you encounter more B's than A's, or more C's than B's, and so on. Let's make it more concrete. Of course, also remove the singlets. And also, you may have repeated diagrams that look equal. But if the labeling is distinct between themselves, then you have to keep both, meaning that you have two representations with the same dimensionality, but two independent ones. And using this method, this is only words now. I'm seeing your faces, and I will make it more concrete just below. And we will revisit all these statements again. So this is a method to remove duplicates, as well as to diagrams that can violate the symmetries, the original symmetry, or the symmetries that are inherent to the original Young tableau. So let's go to the examples. Start with the simplest one, SU2. So let me see, you can see, yeah, you can. So 2 times 2. So this is a fundamental representation. You have learned that a fundamental representation is drawn by just one box. So you label, these two diagrams are both equal, so it doesn't matter if you label the left diagram or the right diagram, it's equivalent. So let's label, in this case, the right diagram. And now the first rule is, let's go back up here. Choose one of the Young tableaus and fill in the boxes. We have done it. It's only one, so only filled with A. And now stack the A boxes of the label diagram onto the other while keeping it a Young tableau. And we should not put two A's in the same column, which doesn't apply in that case anyway. But this is what we are doing. So we are stacking A's in all possible ways. So one of the ways is stacking A here below, which gives rise to this diagram here. And the second is stacking A to the right of that diagram. So there are two possibilities here. And the two possibilities are reflected here. Right? I think this is a fairly trivial one. So you have a completely symmetric, this is a completely symmetric diagram, or completely symmetric representation, and this is a completely anti-symmetric one, which in fact is a singlet, because this is SU2. So you should also cut this. So this dashed line is just to say, okay, this is a singlet. This is not cutting like removing. You don't throw it away. You simply say, this is a singlet. So I can just write 1. So this gives rise to this one. And this, you just use the same techniques as we did before, and I think we did for this, using the counting the hooks and the labeling the diagram as we have learned in the previous lecture, and you realize that this is a triplet, because this, Oswald, yes, so you are trying, yes, So here you would have like so the hooks would be 2, 1. So the hook factor is 2, and this is you start with 2 and then 2, 3 there. And then you have, so the P is 2 times 3, right? So now you have P over H, which is the dimensionality, is 2 times 3 over 2, which is equal to 3. So this is a triplet. This was just to recall procedure. Let me erase. Right. So, right, this was very simple, but there are more rules which don't apply to this one. And let's try to move forward. So let's go to SU3. SU2 is fairly trivial group. So let's, well, if you go to larger representations, it starts being less, increasingly less trivial. But let's now look to the case of SU3. So let's start with the exact same simplest scenario, like two fundamental representations of SU3. So 2 triplets, so a 3 times 3. So recall that the fundamental representation of any SU1 group is always represented by one box. So it's the exact same thing as we have done before. So the only difference in comparison to SU2 is the dimensionality. So you count the hooks. It's the same thing for the hooks. It's 2 times 1. So the hook factor is 2 for this one here, of course. It's 2 times 1. But then the second, you start with a 3 here and you put a 4 here. So it's 3 times 4. So it's 12 over 2, which is equal to 6. And this is this sixplet or sextuplet, whatever you prefer to call it, is also a symmetric tensor. So this a function, a wave function, or some representation, some field of this has 2 indices like ij, and they are symmetric. Now the other one is no longer, it's not a singlet because this is SU3. So in SU2 this was a singlet, but in SU3 this is not a singlet. And then you count and you realize this is the anti-fundamental representation of SU3, as we have introduced before. So you have a bar, and it's anti-fundamental because you can build this, and you have 2 anti-symmetric indices because in the sense that you can build this from a symmetric representation and an epsilon tensor. And the epsilon tensor has 3 indices, and 2 of them are contracting with the 2 symmetric indices. So overall, in the index contraction, when you build Lagrangians, these 2 indices become antisymmetric. And so that is what is reflected in this being a column here. Of course, this is easy to see up to this level. To go beyond, it's a little harder to visualize, but at least for me. But it's but then this is an elegant mathematical or combinatorics description, and everything works neatly, which is really great. Right. So so 3 times 3 equals to 6 plus 3. So if in a not high school, in the when you learn the counting, like I don't know how to say in English, but if it's in terms of group theory, 3 times 3 is no longer 9. So 3 times 3 is 6 plus 3 bar, of course, but which is 9, and that's the point. So what is the thing here? These things, and also 2 times 2 is equal to 3 plus 1, which is 4. But the point here is the following. These things are meant to represent particles in the context of particle physics. Maybe in other contexts, it will represent degrees of freedom in general, which in particle physics represent the number of particles or the number of fields that you have in each of these representations. And when you have a doublet, in fact, you have 2 particles in each of them. And if you have the contraction of 2 doublets, overall, you can have you have 4 particles, but they organize themselves in 2 independent ways, in a singlet way and a triplet way. But let's say the scalar product of the dimensionalities of each of them it has to be the same as like the scalar sum of the dimensionality of all the splitted representations. This is like a sanity check that you can do if you do a tensor product of a big representation. Imagine a 2630 of E6. I'm not talking about exceptional groups, but there are these sorts of representations. Then you do a splitting, and you have like a train of a direct sum of several representations. Then if you sum all of those, and if it gives the same number as the dimensionality of the initial one, then you know that your calculation proceeded correctly. Right. So, but let's now see something that will allow us to have some more possibilities. Now, a 3 times 3 bar. Now you know that the 3 bar from this exercise, it's this column. And now here you use the suggestion that always label with these A's and B's and C's the smallest diagram. We could label with A and B the second one. It would lead to exactly the same thing, but you would have to split it into more representations and at the end cut all of those that are forbidden, that don't respect the rules. But it's simpler to label only one of them. So we label the fundamental one, and now let's stack A in all possible ways, respecting the Young tableau rules. And which ways are those? Again, there are only 2 possibilities here. So you stack A here to the right of the first row, and you cannot stack it on the second one because the row below would be bigger, so it violates one of the rules of Young tableaus. But you can stack it to the bottom of it, but you cannot again stack to the left because once again it would violate the other rules of the Young tableau. So you always write a stack below or to the right of it. And so you have these 2 possibilities. And now this last one is a singlet. And this we have already computed is an octet. This was one of those that we have computed in the previous lecture. So 3 times 3 bar is equal to 8 plus 1, 1 being a singlet and 8 being an octet. So if this is SU3, which it is in this case, this octet can represent, for example, the gluons. So it's an adjoint representation of SU3, and that's why you have 8 gluons of the strong interaction. Right now, and the 3 can represent a quark, and the 3 bar an anti-quark. Now 3 times 6. So now there is still only 2 possibilities because you have a 3 and a 6 is totally symmetric. Once again, you stack A to the left here, and now A to the bottom, sorry, to the first one, which is here. And now you do the counting. So here I've done the counting because it was not done before. So the P factor, you start in 3, and then you increase 3, 4, 5. So the P factor is 3 times 4 times 5. Now you count the hooks. So the first hook, this one is 3, passes 1 through 3, 1, 2, 3. So 1, 2, 3. The second one is 2 because it goes over 2 boxes, this hook, 1, 2. And the last one is covers only 1 box. So the H factor or the hook factor is 3 times 2 times 1. Altogether, it's 20 divided by 2, which is 10. And it's a totally symmetric one. So you have this 10, a symmetric 10. The second one, you know, it's an octet that we have done before. So 3 times 6 equals to 10 plus 8. Now let's have a little bit more fun. Something that already has a B. So we have an A and a B now. So this is a 3 bar times 3 bar. So now it's completely irrelevant whether you label the first or the second. So let's just label the second because it's easier to see with an A and a B. First rule, let's stack A onto the first diagram, leaving B aside for the moment. So what we do is first put A onto here and onto there. These are the only two possibilities, A here and A there. And take the direct sum. We still have B to stack on it. So you take the direct sum, you should put the brackets and tensor product with the same thing. But now this is just to help visualizing things. You cut out the box that was already the A box. You just put this, it's not to remove it, it's just to say, okay, we have already took into account the first row of indices. In this case, it's of one single index. But let's now take into account the second row of them. And we have to stack B onto the left and the bottom of both diagrams. So you can imagine that the number of possibilities will grow now. And here they are. So B, where can we put them? We can put B first next to A, so B here. We can put B below A, so here. And you can also put B on this third one. So these first three ones are related to put B here, here, and here separately. And on the second one, it's easy because this is already a singlet. We are talking about SU3, and here you don't remove singlets when you are doing this playing with young tableau. Don't remove singlets, only at the end. Only at the end. This is very important. Let's place B, and there's only one possibility. You cannot place it below because it goes above n. It would get 4 boxes, and you need to have at most 3 boxes. So B can only be put to the right of the first box. So here it goes, B here. Now I will go up and read another rule. Sorry, Mark, you were copying something?
No, no problem.
Okay.
Once you get there again.
Sure. Now, so what we have done was this, stack the A boxes onto the label diagram, and then repeat the procedure for the B boxes, and C and D's. And now read. Now it's what we are going to do is this purple and this blue thing here. Read each diagram backwards, starting with the first line. This is the first line backwards, then second line backwards, etc. And so this is we are going to read, and we read, and then what we do is this: delete all diagrams in which at some point is not in total. It's when while you are reading, you are filling up, let's say, a database with A's and B's and C's. And if at any given point you have more B's, so let's say a letter that is lower in the alphabet, you can do this with numbers as well, but I think it's easier with the, to not confuse with hooks and the p factors and so on. It's easier with letters. It depends. Some references use numbers, some references use letters. But the rule that I suggest is if a letter that is below in the alphabet comes more times before a letter that is above it, then you remove that diagram is a repetition of something. It's a double counting of something, or it's an illegal diagram, let's call it. So, so at some point, if you encounter more B's than A's, you stop the counting there. So you stop going backwards in each line. So you go line by line. You stop the counting there, and you say, okay, this diagram is illegal. So you cut it. For example, here are 4 examples. If you read backwards and you have the sequence A, B, this is all fine. Bear in mind that this sequence here, this is not of the order that you read in diagram from backward. This is the order you read and you fill in this data, let's say. So I read, gives me A. Then I go to the second line, starting on the left, another A. Then I end the diagram with a B, perfectly fine. There was never, ever a B, more B's than A's. Second possibility, you read A, and then you encounter a B, and then you encounter another A. Also, everything legal. There was never any instance where you would have more Bs than As. Now imagine you start with a B. So you get into the first box and you immediately find a B. You don't even need to go into the A's and C's. So you already found a B. It's already gone. So you remove this. Now imagine that you have another, you start with an A. So far so good. You go to a B. So far so good. Then you encounter another B. Okay, you break it here. You stop. You don't have to carry on counting. It's an illegal combination. You remove it. So, oops, no, this is not it. Okay, so you remove singlet columns also. Yeah, exactly. And if you encounter diagrams that are of the same structure, but different orderings of A's and B's, still legal orderings, you have to keep both. If you have diagrams which have the exact same one, if I'm not wrong, you should remove them. So this is a method, as I said, to remove duplicates and so on. So let's see what happens here. So you have just put the B's now on these diagrams, and you count like this and then like that. BA, it's already illegal. So you have, when you start counting, you have a B before having any A. So this one goes away. It's signaled here. Now the second one, you read A, fine, B, fine, A, B. Okay, you never have more B's than A's. So this diagram is good to go. Now let's go to the third diagram. You have an A, okay, great. Then you go to the second row, there are no letters. Third row, a B. Oh, good. This is a valid diagram. Now you go to the last one. You start and you crash immediately against the B, so you stop and you don't even bother to carry on. So the last and the first diagram are to be removed. And so now you can remove the labels. You no longer need them. And you write the two remaining diagrams. And you identify the singlets. Now let's identify the singlets. So there is only one singlet here. So you can now at this stage, at the end, you can remove these singlets because you don't need this for the counting. And the final result is simply this box, this square box of boxes and fundamental representation. So this, it's a fundamental 3 already, and it's a symmetric by definition. And then you have the second one, which you need to count. So once again, the hooks, I think this is 1 here. This second hook is 2. 1, 2, 3. So it's a 3 here. And 1, 2. This hook, you have a 2 here. So the hook factor is here. And now, again, it says you 3. So you label 3. Grow to the right, 4. Lower bottom, to the bottom. So you have a 2 here and a 3 here. Note that this 3, it's valid for any of the directions. You lower, it's lowered 1 by 4 and grows 1 by from 2. So even if you grow these young tableaus in this left justified and not allowing rows that are below, so larger rows or bigger rows below a small row, if you will follow these rules, this will always hold. Okay, so P is 4 times 3 times 3 times 2. You do the P over H and you conclude this is 6. But this is antisymmetric. This has antisymmetric indices here. So this is a 6 bar. So the bar doesn't mean antisymmetric. It just, you define the other one as a 6. So you define this one as a 6 bar. Of course, what is bars, it's up to, you can say, okay, the fundamental is with a bar, but that's not the convention. Right. Okay, another example. This is a little bit lengthier. So I'm giving this example so that when I ask you to do this with SU5 and SU6, you can follow the rule. I've already done the examples that I want you to do. And so I think that most of the information is here. So 8 times 8. This was when I did my group theory course in the first year of my PhD. This was my take-home exercise was this. Do 8 times 8. Well, one of those. So do 8 times 8. again, two equal young tableaus. So let's choose to label one of them. I prefer to label the diagram that is on the right, because it's easier to visualize the stackings towards the left, let's say. So let's start stacking only A's. So that's why you can put already outside of it something. So you remove the A's and you leave B only. And let's put all possible combinations of A's. So you can put, now you put the A's, you can put one at a time, but that will grow your, you could do this way, like keeping one here and cutting this one like that. But okay, let's be, with two indices, it's still feasible. So you put, you can put two A's here, which gives this. You can put one here and another one there, which gives this possibility. You can put one here and then another one below, which gives this possibility. And also one here and another one below, which gives this possibility. Right? So I think this is intuitive to see here. So this is, there are no more possible legal combinations, let's say. Now let's multiply this by, so we still have to act the B indices on it. So to do so, you will put a B, so it's only one. So you can put, starting with the first diagram, you can put a B here or a B there, or, well, not or, and. It's one possibility here, the second one is there, and the third one is there. So this is the first, this is the second here, and then you have the third with B there. Now to the second diagram, you can put a B here, or you can put B there, or you can put B here. So there you go. So the second, so B here, or B here, or B here. So these three possibilities. And there is also an important rule that I think is written above. You cannot have a column with repeated labels when you do this in the product, one of the product of the diagrams. So you cannot have A on top of an A or B on top of a B and so on. Now for the third diagram, so B, you can put B here or a B there. You cannot put below because it would go over 3. So there are only these two possibilities. And finally, so you see, this is a long one. And finally, where can you put B here? You can put a B on the first one, or you can put a B below this A. These are the two possibilities. Again, here, a B here, or a B there. Okay, now let's look into the allowed combinations. It's already written here, but let's analyze this. Yeah. So the point, well, the point is the following is to make sure that you don't miss anything. You write, and then it's the easiest way to not get something wrong. Of course, maybe the likelihood of getting wrong is not that high, but it's still non-zero. So I would recommend to put all of these all possibilities, and then you see one by one and you remove them. I think that's the best. Okay, this is easy to do when you have a tablet, of course. If you are writing on paper, you cannot. Actually, 2 days ago, I was working and I forgot my pen, the tablet pen at home. And then I asked for João, so my student, I asked him a piece of paper, and I was using the piece of paper. But then I picked up my paper, and I was looking for the options to select and to paste, and no, this is not working. So of course I understand that, but I really recommend you to write all possible combinations here. What you can do if you want to save some time is that you write the combination here, and you already, okay, this is no longer legal, so you cut, And in the second line that will follow below, you will already not introduce that one. If it's a longer one, for example, if you have to do like 3, 4, or 5 iterations, the first iteration it should be there, and make sure that. But for example, don't do the same mistake that I have done at some point, which was I decided to start removing singlets from the beginning. And then I removed combinations that were no longer singlets, would be no longer singlets. Okay, the columns would be removed, but then the positions of A's and B's would be such that I was removing valid contributions. And at the end, I was missing 1 or 2 representations because of that laziness. So that's the thing. I thought, okay, this is obvious. This is a singlet. Let me remove and let me keep only the boxes that the final, let's say, the final structure resembled more or less the same thing, but then the independent representations were not taken into account. So like imagine you have 2 tens or 3 tens. You can have 3 different combinations of A's, B's, and C's, and so on. And I could not see that by removing the singlets from the beginning. So the singlets absolutely only remove at the end. That's the safest way. The other ones, at least keep them once. If you don't have a tablet, keep them once at least. And if you have a tablet, I recommend to keep everything as you go. Okay, good. So, of course, so this is AAB, this is legal, AAB, legal, BAB, of course, illegal. You start with the B first. ABA, good, AAB, good, B, starting B, legal, ABA is good, BAA, no, and ABA, this is also good. Okay, I think I was a bit fast, but I think you understood it. This is nothing special. So now, write everything still with labels. Now you remove the ones and write everything with the labels. And I think here it will become evident what I meant before. So note, you have this one and this one. You have this same one happening twice. But look, you have 2 different combinations of A's and B's. And both are legal. So you have A, A, B, and here you have A, B, A. So these are 2 same dimensional representations, but they are different. So you will see this is going to be a template of SU3, but you have 2 tens inside of this tensor product, which must be taken into account. So now you identify singlets, and here, yes, now you can remove the columns of 3. So you have 1 here, another one there, and another one there. And you finally write, and of course you have 2 columns here that you should also remove and replace it by 1. So this and this, you replace it by 1. So now you have the final ones here. And again, let me just say, I was saying the combinations here, yes, it was valid what I was saying, but here is where you clearly see that you have 2 which look the same, but then you have AA and here AB. So these are different ones. This means that you have different contraction of indices because the B's are coming from the second row, A's are on the first row, so it's clearly different index contractions that are happening. So let's compute the dimensionality. Just following the same procedure of this one. Of course, this is with more, you have more hooks and more. So P starts in 3 and grows here and decreases in this direction. The hooks, so it's 1, it's 2 hooks, it's 4 here, it's 5 here. So 1, 2, 3, 1, 2, 3, 4, 5, and 1 here. So you compute this, and this gives 27. So this is a 27 plate of SU3. You do the same with this box here. So this is actually the template, not this one. These are octets. So you have 2 octets here. You do this, and you arrive at this conclusion. You have 10 plates. And since you already know that these here are octets, and you also know that this is a 6 plate, sorry, no, a 10. This is the 10. Okay, so this is the 27. Exactly. This is the 27. This is the 10. Exactly. This is 8. This is 8, and this is yeah. This is also 10. These two are 10s, but one is a 10, another one is a 10 bar. One is symmetric, another one is anti-symmetric. So this is totally symmetric. So this is the one that is anti-symmetric. In fact, remember, so a tensor, you can always represent this in a symmetric and an anti-symmetric part. And this is actually what is being done here. You are separating a 10, which is a reducible representation, into two irreducible representations, a symmetric part and an anti-symmetric part. And so this is what you can write at last. So 8 times 8 is equal to 27 plus 10 bar plus 8 plus 8 plus 1. So 8 is a real representation here. So this is all, they are all equal but independent. Yes? In the first, where do you think there is a 3 missing? Key 5, 4, 2, 1. Yes, this is right. So this is the hook. So yeah, you will. This is very easy. You will you will understand this. But I tell you. So the hook, it's you pass a line here, and when you have the vertex of the hook, you count. Okay, for how many boxes did this hook pass through? So how many boxes you see here? One, right? And how many boxes this hook is covering? 2. And how many boxes is the hook covering? And this one? 5, right? And this one? And this one? Okay, so this is how you label it. So now you know how to do this. Yes. Here, yeah, here it's, but this is a different thing. This is the P factor. You yeah. Yeah, but it's different because you have a different structure of the box. So this is not always. So you have here, this passes over 2, 1 here, 3 boxes, 4 boxes, and so on. Osvaldo.
I'm getting a bit about the anti-symmetric ones and symmetric. So why are the 8s not symmetric? We have those before as well. But I don't see if they have the different rows, then those rows are anti-symmetric, right?
Yes. So we have these two things here which are anti-symmetric. But so okay. So these two indices here. These ones are symmetric, yes. So this has to do with the way you can construct an octet from another representation. So in principle, you have some larger like in the same way that you can construct, for example, so an anti-fundamental psi I, you can construct psi I jk psi jk, where this is why you have the anti-fundamental like a column with like 2 jk indices, so which are anti-symmetric because of the anti-symmetry that you have here. For the octet, it's there are more, but yeah, you need to take into account symmetric and anti-symmetric indices. Yes, of course. This is what is meant here. So these two possible, but this has to be taken into account in terms of possible contractions with group invariants and other representations. Vai vir uma aula aqui. Ok, tá bem. Tá bem. Okay, we will have to change room. This is insane, but okay. Oswald, we will talk about that because they want to start. So, guys online, try to connect again. So let's make a break, and the break is going to be try to find another room for the... Como? Não percebi. Está bem, está bem. Sim, 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 sim. Podemos falar disso tudo. Mas tenho que resolver primeiro isto agora. So guys, try to connect again. I will stop the recording, and in fact, and we'll start a new recording after. Okay, guys. See you in a few minutes. Stop cloud. Yes.